Hello to all my young friends who are studying in intermediate and they are watching this video. Welcome to lectures of GTK Academy. In our previous video, we had covered the topic scalars and vectors. I hope that you would have seen that video. If you have not seen it, please do see that because that's a very important topic. Today, we are going to cover a new chapter, a new topic, and the name of the topic is motion in a straight line. As I have already indicated in previous video that henceforth I'll try to cover the whole chapter in one video, except the cases where you have one or two topics in a chapter which are quite important. Those topics I'll try to cover separately and post it in different videos. Apart from this, my endeavor will be, while covering any topic or any chapter, that all your concepts are clear, definitely along with some good questions which again reinforces your concept. And here I extensively use PPTs, animations and figures just to make it easy for you to understand, and the time should not be wasted because if I start drawing the figures, it's going to be unnecessary wastage of time. So now, without wasting any time, let's start our topic today, motion in a straight line. Now, what are we going to cover here? We will cover frame of reference, equations of motion, and the graphs. Now this chapter, motion in a straight line, is extremely important, and apart from that, all these topics are very important and they are extensively used across. Now let's start with our first topic, that is frame of reference. What is a frame of reference? To make it a bit interesting, let me start with the dictionary definition of frame of reference. Now dictionary says that at a particular set of beliefs, ideas or experiences, they affect how a person understands or judges something. Now every person has been brought up in different environment. He has different set of beliefs, he has different ideas, he has different experiences. Owing to that, he judges a particular thing. That is the reason. Probably one person may like a particular thing and the other person may dislike the same particular thing. Now the reason is both have different frame of reference of mind while viewing that particular thing. So that is the dictionary definition. Now let us slowly drift toward physics. Before that, now here in this photograph, you can see a building, and this building is Empire State Building of USA, which was the tallest building some time back, but now certainly other buildings are even tall than this. Now if you just stand in front of that and see it, it will look like this. You know, you are going to be overawed by the height of this building. So you will have a feeling. But if you look the same building from an aircraft just before landing, it will appear to be a tall structure, but it will not have the same feeling which you have while standing in front of the building. But if the height of the plane is, the altitude is very high, it may not even be visible enough. So if you see from these three places, your feelings are going to be different. The object is same, but your feelings are different. You will have the different experience from three different places. Now let's come to physics. What is a frame of reference? That is a system with respect to which position and time coordinate of an object or an event can be described. Like, suppose this is a point P. Now where is it P? How do you describe that? For example, if I ask you, where is the railway station? Definitely your place may be having a railway station. So you will tell it's 5 kilometers. What does that mean? 5 kilometers. That means 5 kilometers from the place where you are living. So this place is a reference point. So point P has to be defined in with respect to a system like we have x, y, z axes. So the coordinates of P will be defined as x, y, and z. So position of P at any time can be expressed in terms of coordinates x, y, and z. Say at t1 it is x1, y1, z1, but t2 you have x2, y2, and z2. I hope I'm clear with this. Now let's move forward. Now if we have observer in different frame of reference, we take the case 1. Our frame of reference is on the ground. That means you are observing from the ground. Ground is your frame of reference. There is a car which is moving towards you with a speed of 100 km per hour, and then there is an aircraft flying like this with a speed of 500 km per hour. Now how will the car appear to observer? It will appear coming in this direction with a speed of 100 km per hour, and the aircraft will appear to move in this direction with a speed of 500 km per hour. Now if the frame of reference is inside the car, that is observer is inside the car, then what will happen? The aircraft will appear to move towards him with a speed of 500 plus 100, that is 600 km per hour. The car will appear to be stationary because he is sitting inside the car. Until and unless he sees outside, he will not have a feel whether the car is moving or not, although it is moving at 100 km per hour. So car will appear to be stationary to him. However, the ground will appear to move towards him with a speed of 100 km per hour. You would have seen when you travel in a car that trees and the objects on the ground appear to move towards you. They are all stationary. Third case, observer is in the aircraft, that is frame of reference is the aircraft. Now the car will appear to move towards this observer with a speed of 100 plus 500, that is 600 km per hour, and the ground will move towards him with a speed of 500 km per hour. That will appear to move, and the aircraft will appear to be stationary because he is inside the aircraft. That means from these three examples we conclude that a physical quantity has different values when measured by observer in different frame of reference. Your speed of car was different when viewed from aircraft, when viewed from the ground, and when viewed from inside the car. So the same uh, uh, physical quantity has different values when measured by observers in different frame of reference. Now, frame of reference can be inertial and can be non-inertial. What do we mean by inertial? By inertial, we means that Newton's first law correctly describes the motion of a body. What is Newton's first law? Every body will continue moving, or if it is in a state of rest, it will continue in that position until and unless exerted by some external force. Every body continues to be in its state of rest or of uniform motion until and unless there is some external force acting on the body. So, for inertial frame of reference, Newton's first law correctly describes motion of a body. Now, such frame of reference are either at rest or they are moving with uniform velocity. Now, what is non-inertial, frame of reference? Here, Newton's law does not hold good. Means Newton's first law does not describe the motion of the body. How is it possible? You know, that Newton's laws are applicable at one place and not applicable at one place. No, actually they appear to be not applicable. Now, I'll clarify that this kind of frame of reference are either accelerated or they are rotating. Now, if you want to make Newton's law hold good in this frame of reference also, then we have to consider some mysterious force which is called a pseudo force. Now, what is that? Let me clarify that with some examples. Suppose this is the train and we have an observer sitting inside a train, and this is a bob which is hanging from a ceiling by a string. Now, if he observes this bob, it is at rest, it is just hanging. There is no force, so there is no movement. Even if the train is moving with a constant velocity, still it is at rest because there is no force on the bob. This is what we call inertial frame of reference. That is, Newton's first law describes the motion. That means in this case it is at rest because there is no force. And here also, since velocity is constant, there is no acceleration, there is no force. So that is at rest. However, if the train accelerates, then what happens? Immediately this goes backward. Or if the train decelerates, that is, there is a retardation, then it moves in this direction, right? So what happens? This observer sees that it is coming in this direction, or here he observed that it is going in this direction. So apparently there is no force acting on the bob. So how is it possible that it is moving in this direction or in this direction? So that means Newton's law doesn't correctly describe the motion of the body. So this is a case of non-inertial frame of reference. Although, if you are an observer, you may feel that it is accelerating or there is a retardation. So you may be able to, visualize, since there is an acceleration, it is going backward. But observer, by observer, I mean there is a camera here and you are watching from a distance this bob through a camera. Now, camera shows that bob is at particular position. You are not able to see the acceleration or retardation of train. Your camera is focusing on this bob and suddenly bob has started moving and there is no apparent force. Bob is moving in this direction or bob has started moving in this direction and apparently there is no force. So this is non-inertial frame of reference. Or if you have a disk which is rotating and you have an observer, that is a camera fixed here, and camera is focused on a coin which is placed here. A coin is placed here. Now, after some time, because of the rotation of this disk, observer comes at this place, at this position. So, the coin should have been at this position, because whatever the distance which was there between observer and coin, say it is d, here also it should be same. It should remain same. But what happens that if the disk is not smooth, not very rough, it's smooth and the rotational speed is very high, this coin will try to move in this direction, and after some time coin will reach this position. So to this observer or this camera will show that coin is moving in this direction, which is shown by this red arrow. So this will be the movement of coin seen by an observer. Here also observer will think that there is no force. When there is no force, how is this coin moving? So this is also non-inertial frame of reference. In all the three discussed cases, if we want validity of Newton's law, we have to assume a pseudo force, because in all these three cases you are seeing movement of a particular body without any force. So it appears that Newton's law is violated. So if you want that Newton's law should hold good, then we have to assume a pseudo force. How are we going to assume that pseudo force? A mysterious force. That means in this case, when the bob is moving in this direction, you have to assume that there is some pseudo force, some mysterious force which you are not able to see. It is acting in this direction, or in this case it is acting in this direction, or in case of coin it is acting in this direction. Now pseudo force is always against the direction of acceleration. Let's see how. Here you have acceleration in this direction. So the pseudo force is in this direction. Now if the acceleration is a and the mass of the bob is m, then the pseudo force is ma in this direction. If the force retardation is a in this direction and the mass is m, the pseudo force ma is in this direction. And here, when anything is doing a rotational motion about a center, say, and the radius is r, there is a centripetal acceleration which is towards the center. If the velocity is say v, the centripetal acceleration is v square upon r. So here on coin, since coin is you know uh, doing a circular motion, so there will be a force in this direction which is equal to v square upon r, where r is the radius of coin. So the pseudo force will be in opposite direction, and that will be equal to m v square upon r, where m is the mass of the coin and r is the radius of the coin. What we said that these are non-inertial frame of reference, that is for a observer A. If our observer is inside the train which is accelerating or there is a retardation, then these frame of reference are non-inertial frame of reference. So here it appears to the observer that Newton's laws are violated, and he is not able to understand why this bob is moving in this direction or in this direction, and then he has to think of some pseudo or mysterious force. However, if an observer is outside like this B, who is in an inertial frame of reference, he is able to see the picture in totality. He is seeing that since the train is accelerating, owing to the inertia, this bob is going in this direction or in this direction. So for this observer B, who is in inertial frame of reference, there is no violation. He does not find any violation of Newton's laws. Similarly, in the case of disk, the observer who is sitting on the disk finds that Newton's laws are being violated because that's a non-inertial frame of reference. However, if an observer is outside, say in this position, in an inertial frame of reference, he is able to see the picture in totality. So he finds that since the disk is rotating at a good speed and friction is not sufficient to hold the coin because disk is quite smooth, that is the reason coin is moving outside. There is no violation of Newton's law for this observer because he is in inertial frame of reference. But since A is in non-inertial frame of reference, he finds violation of Newton's laws. So frame of reference inside the accelerated and decelerated train or a rotating disk, they are all non-inertial frame of reference. Now a frame of reference attached to Earth can be considered to be inertial for all practical purposes. Suppose our frame of reference is attached to Earth like this. This is an inertial frame of reference because what we discussed, that inertial frame of reference is either at rest or they move with uniform velocity. So for if the frame of reference is connected to Earth, we can assume it is a inertial frame of reference, but it is not so. Precisely, that is also not inertial because Earth has axial and orbital motions also, because Earth is rotating about its axis like this, and then Earth is also rotating and has its orbital motions around the Sun. Owing to these motions, there are forces, there are accelerations. So precisely the frame of reference which is connected to Earth, that is also not inertial frame of reference, but for all practical purposes we can consider it to be inertial frame of reference. Now, if a frame of reference is inertial, then every other frame of reference which is in uniform motion relative to it is also inertial frame. For example, this is a frame of reference and it's an inertial frame of reference. Then any other frame of reference, suppose this is another frame of reference and it is moving with velocity v with respect to this frame of reference, then this is also an inertial frame of reference. If this is an inertial frame of reference. Let's take some interesting example. Now consider an observer in a lift observing a block placed on a weighing machine like this. That means the frame of reference is inside the lift. Now we'll consider few cases. First case, lift is stationary. When the lift is stationary, what kind of frame of reference is that? That is inertial frame of reference. Now what will happen? This block will have some weight, say mg, and it will act downwards. And because of its weight, it will press the weighing machine and it will exert a force on that, you can say W. This W will be displaced as the weight here and it should be equal to mg. Now, since the block is pressing the machine downwards, so as per Newton's third law, the machine will exert equal and opposite force on the block in the reverse direction, that is R. So that means R will be equal to W. Now just see the block. Now for the observer, block is stationary and it is because the lift is stationary. Now you have two forces there. One is mg downwards and the other is R upwards. So since the block is stationary, R is equal to mg. Now if this is equation 1 and this is equation 2, so from 1 and 2, W is equal to mg. So the display in machine is going to be mg, which is the correct weight of the block. Second case, if the lift is moving with constant velocity, again this is also a case of inertial frame of reference. In this case also, correct reading will be displayed here. This is the actual weight and same is shown by the reading here. Now if the lift starts moving with an acceleration a, what happens? First of all, what is the frame of reference? It is non-inertial frame of reference. What will happen in this case? Actually, if you would have experienced, I think all of you must have experienced, when the lift goes up with an acceleration, we feel a bit heavier. So here also the reading will be a bit more than the actual weight. That means the force with which this block is pressing will increase and hence will be the reaction. That means R dash is equal to W dash. Now, as per the observer, there is no force in this direction. Then he will think, how come the reading is increased? Because how any reading will increase? Suppose this is your weighing machine and you have a block here. So whatever its weight will be displayed here. Now display will only increase if you put some more weight here or you put force here. Now what do we do to solve this? We have to apply a pseudo force. and pseudo force direction will be reverse the direction of acceleration. Now if you analyze the forces on block, one is your reaction R dash, mg downwards, and then a pseudo force ma in this direction. Now for equilibrium of this block, because for observer the block is in equilibrium, R dash should be equal to ma plus mg.